Hi everyone, welcome to Astronomy 236. We have another big lecture today, in which we will go through the lives and deaths of stars, and we'll go through how they evolve from clouds of gas eventually to dead remnants at the end. And the theme of today is going to be the fight against gravity. Throughout their lifetimes, stars are locked in a constant battle against gravity, which is trying to collapse them down as far as it can into essentially singularities, into black holes. But the stars fight back and they keep themselves larger as long as they can. And the theme of this lecture is just going to be, during each phase of the star's lifetime, how does this fight look? How does the struggle against gravity do? And what is the cause and what are the effects of this struggle? So to remind you, stars form from clouds of gas. So here's a simulation of a cloud of gas, which starts off uniform with a few small perturbations. And eventually, if you let gravity do its thing, then parts of that cloud will collapse down into relatively compact regions. And these regions look something like areas of the galaxy that we can see today. So here are some really nice images from the Hubble telescope and from the VLT in a couple of slides. So this is a famous nebula called the Eagle Nebula, and this is probably one of the most famous images taken by Hubble. It's called the Pillars of Creation. And these three pillars are basically just clouds of dense gas. And what's amazing about this image is you can see so much detail. You can see these small little points sticking off. These are relatively dense regions where stars may be actually starting to form. You can see the ripples in the cloud, how it's being blasted and how some of the gas is evaporating away. So this is a stellar nursery. Eventually, all of these pillars are going to collapse down and be stretched into very thin, long regions, and then those regions are going to have little knots appear in them, and those regions are going to become stars. Here's another really beautiful image from Hubble of the Horsehead Nebula this time. This is another similar star-forming region, and you can see kind of this amazing detail in the clouds of gas. It looks like a cloud you might see in the air. And finally, here's a third example of a molecular cloud. This one's a little bit different because it has a lot of dust in the way. So it doesn't let light through, and it doesn't emit much light in the optical wavelengths where we're looking. But what you can see is that it blocks the light from stars in the background. So instead of seeing the gas itself, you can see its shadow, essentially. And this image is not taken by Hubble. This was taken by the Very Large Telescope in Chile. So once we have molecular clouds that look kind of like the ones that I just showed you, they can collapse down even further. So if we zoom into the simulation here, you can see that smaller and smaller regions are forming. There are more of these small point-like densities, and eventually they start forming stars, which in this example are shown by these little white dots that are flying around and getting ejected from their birth regions. So what is the process of this? How does this actually happen? So to think about that, we'll need to remember that when gas is compressed, it gets hotter. I've shown this video a couple of times now. When you plunge down and compress gas in a tube and you have some ignitable material, it can actually flash it into igniting because you've heated the gas so much. So the same thing happens for gas that's collapsing down into stars. Without any other energy processes happening, if you just collapse a gas cloud down, it will get hotter. The temperature of that cloud will go up. And another thing that we need to know about the process of collapsing gas is that gases exert pressures, and hotter gases exert more pressure, more force on their surroundings than cooler gases do. So this force is eventually going to be something that stars use to balance against gravity. So here's an example of what this looks like. So this person is taking some red liquid, just red colored so that you can see it more easily. They're putting it into this little straw, which is going to go into an airtight vial. So the only way for air to get in and out is through this straw. So what you can see is the water is completely clogging it up. So when this person puts this vial into hot water, the air inside of it expands and pushes that little piece of water upwards. And when they put it into cold water, the air contracts and there's less force, so it can no longer push that little particle of water up against gravity. And when you bring it into the heat again, it pushes it upwards. So hotter gases push stuff back, and they actually push hard enough that you can oppose gravity. So the increased pressure does this exact same thing in stars. And what it ends up doing is it slows the contraction. So instead of the gas essentially free falling as it was before, it's now falling a little bit slower because as it collapses the gas even more, it generates more heat. It generates a higher temperature in that gas, which then pushes backwards against gravity. But this can't hold it in steady equilibrium for very long. And the reason is gravity is always going to win this battle because the amount of heat that it generates will eventually be radiated away. So remember that hot, dense objects emit their own radiation, like this black body radiation that you would see from the stove. So when a star, a protostar, a cloud of gas that's been collapsed very small, gets hot, it will radiate away some of its heat via black body radiation. And that will cool it down because it will have taken some of the energy that it was using to keep itself hot and hold itself up, and it's irradiated that away into space via light. So the contraction continues, and it continues, at a relatively similar temperature for a while. So after a few zigs and zags, and after a few different changes in how the process actually goes down, which I'm not going to get into today, eventually gravity collapses the cloud down enough that the core temperature, the temperature in the very center of that cloud, rises to millions of degrees Kelvin. So Kelvin is a unit of temperature. It's similar to Celsius, but it's offset. So 0 degrees Celsius is 273 degrees Kelvin. But when you talk about millions of degrees Kelvin or millions of degrees Celsius or millions of degrees Fahrenheit, it's all pretty similar. They're all in the millions of degrees. So very, very hot, regardless what your temperature scale is. So when you do this, particles in the core of the star start moving around enough that they can start smacking into each other and fusing. And this is the process of nuclear fusion. So in this example, I've shown two protons, two hydrogen nuclei, smash together, stick together, and end up as a helium nucleus and emitting a little bit of energy as well. And this process starts happening over and over and over in the cores of stars, and it creates enough energy to heat the star from the core, make the gas push backwards against gravity, essentially hold it in a perfect balance between the fusion going on in the core and the gravity pushing down from outside. And this balance lasts a long time. This is what we call the main sequence, the kind of main lifetime of a star. This is where our sun is right now. So if I wanted to talk about how long this actually lasts, what I'll first show is I'll show the timescale for forming stars. So if we start counting our clock upwards at the time the cloud starts collapsing, it takes maybe 100,000 to 1,000,000 years for the cloud to build up enough pressure and to get compressed enough that small regions start to heat up and look like stars to our telescopes, even if they're not fusing hydrogen yet. And it takes a little bit longer, maybe 10 to the 7 years, so maybe 10 million years or so before stars like the sun start actually fusing hydrogen in their cores. But this time scale, however long it may seem to humans like us, pales in comparison to the lifetime of a star on the main sequence when it's fusing hydrogen. So the hydrogen fusing lifetime of a star like the sun is about 10 to the 10 years or 10 billion years. So 1,000 times longer than the entire time during the star's formation before it was able to start fusing hydrogen into helium. So here's one of the ways that we visualize stars. I'm gonna show diagrams like this throughout this lecture. So it's going to talk through it a little bit. It's a little bit confusing because of some choices that astronomers make. But on the y-axis, we're showing the brightness of stars. And we scale it to the brightness of the sun. So in this example, the sun sits at a brightness of 1 because it is exactly as bright as the sun. If you go up to the top, then we have stars that are much brighter, maybe 10,000 times brighter than the sun up here. On the x-axis, we're showing the temperature of the star. And here's where it gets a little bit confusing because astronomers like to show this backwards. This is for historical reasons, before we really figured out what the physics was happening in the stars. So over here on the left, we have temperatures of 30,000 degrees Kelvin, which is way hotter than our own sun. These are relatively blue stars because blue objects are hotter than red objects. Over here in the middle, we have about 6,000 degrees Kelvin, which is around where our sun is. Our sun's temperature is about 5,700 degrees Kelvin. And over here on the right, we have stars that are about 3,000 degrees Kelvin. So these are relatively red looking to the naked eye. And it turns out that when stars are burning hydrogen, they behave fairly similarly. And they all fall on this one region of temperature brightness space. So if you know that a star is burning hydrogen and you know its brightness, you should be able to know its temperature as well. And it has to fall along this curve here. And we call this curve the main sequence, the sequence during which stars spend most of their lifetimes, because this is when they're spending most of their energy burning hydrogen. During the process of forming the star starts off up here in this top right corner, where it's really big. So therefore it's got a large surface area to emit light from, and it's relatively bright. But it's also very cool because it hasn't yet compressed itself enough to start emitting lots of light. So it kind of falls down here and then makes a couple of wiggles and ends up on the main sequence. So once the star is here, once the sun is here, it stays here pretty similarly. It doesn't really move around much for the next 10 billion years or so. So I've been talking about how long stars stay on the main sequence, how long stars burn hydrogen. And I've been talking about the sun, and the sun burns hydrogen for a very long time. But this isn't always the case. It turns out that some stars burn hydrogen for much less time than the sun, and some stars burn hydrogen for much more time than the sun. And the reason for this is because when you balance fusion and gravity, when gravity is stronger, fusion has to be stronger as well. So if you have a more massive star, gravity is pushing down harder on the core, and that's heating the core up because more compression means more temperature, and that's causing fusion to accelerate. The hotter you are, the more fusion can happen. And when you have these really, really massive stars that push down very hard, it means fusion goes into overdrive, and the fuel from the star is burned up very quickly. So this graph here is showing the lifetimes of stars as a function of their mass. So on the y-axis is showing the mass of a star. So let's imagine up here we have a really massive star, 150 times more massive than the sun. It does not live very long at all. It burns through its fuel extremely rapidly. Down here, we're looking at time scales on the order of 20 or 30,000, maybe 50,000 years. Again, that seems like a long time to you and me, but in astronomical terms, that's practically the blink of an eye. Over here, we have our sun, which will last something like 10 billion years as it burns its hydrogen relatively slowly. In fact, it will last for almost the entire length of the universe today. So there are stars that could have been born at the very dawn of the universe, which could still be burning their hydrogen fuel today, because stars can last longer than 13 billion years in terms of their hydrogen burning, especially these low mass stars here. And when you go down to the very smallest stars, the stars that are only about 1/10 the mass of the sun, they can burn for mind-boggling amounts of time, trillions of years. So it really makes a huge difference how much mass you have for how long a star can stay on the main sequence and keep burning hydrogen. So let's fast forward through all of that hydrogen burning time. It's, of course, our favorite time in a star's life because it's the time that our sun is in right now. But for astronomers, it's relatively boring. Not much happens. You can't really tell what's going on with the star, and you can't really tell where it is in its age. So let's just fast forward through those 10 billion years of evolution for our sun. And it's burning hydrogen into helium and burning hydrogen into helium. And it's building up more and more helium in its core, and it's losing hydrogen. And eventually what happens is the core is almost entirely helium, and it's no longer able to fuse. So why is this? It turns out that hydrogen is the easiest element to fuse into another element. All you have to do is smack them into each other at relatively low speeds. If you want to do the same thing for heavier elements like helium, they need to be going even faster, so they need to be even hotter. And on the main sequence, the core of our sun is just not hot enough to cause helium to fuse into heavier elements. So what happens when we run out of hydrogen? what happens is the core starts collapsing because now we no longer have the energy being produced. We're no longer fusing hydrogen into helium, so gravity starts to take over again. Gravity starts to push this core down. Now, it's a little bit counterintuitive, but when this happens, that actually causes the outer layers of the stars to expand. And what goes on is when you compress the core down, it gets hot enough to start burning helium now. And it also gets hot enough to start burning a shell of hydrogen around the core. And when these two things happen, they don't happen at the same time, they happen sequentially. First, there's a shell of hydrogen burning all around the core, and then eventually the core of helium starts to burn. They end up producing a lot more energy than they ever could on the main sequence because fusion is now in overdrive. Now we've compressed the core down a lot. And what that does is it keeps the core small and compressed, but it causes the outer layers of the star to puff up and expand to very large radii. So the star actually physically gets much, much larger than it was before. So here's a way to kind of conceive of how massive these changes are in the sun structure. So here's an image of the sun today. And what I'm going to do is I'm going to zoom out. So now this image is to scale the sun. And you can see that little dot in the center of the image here. When the sun runs out of hydrogen fuel and eventually goes through this evolutionary process after it's run out, it will puff up to about 200 times its normal size. So this would be the scale of the sun to scale. And for comparison, this is now, the star is now almost as large as the distance from the Earth to the sun today. So if the Earth is still here and it's in its same place, we would basically be grazing the sun. So it won't be a great place to be. So this process happens for pretty much all stars that have ever evolved enough to run out of hydrogen. And I say this because we don't actually have any examples of stars that are lower mass than the sun by quite a bit that have ever actually run out of hydrogen. Every star less than about 70% the mass of the sun is still burning hydrogen because it's just the universe is too young for it to have done anything else. So we have essentially no way of testing what happens for these lower mass stars, although we can make some predictions. But I'm going to focus on stars that actually can evolve in the length of the universe today, and we actually can see what happens for them. So what will eventually happen is these stars will fuse hydrogen to helium, they'll run out of hydrogen, and then they'll start fusing helium into heavy elements. And this process of fusion will keep going on as long as the star's mass is enough to compress the core enough for it to keep going. And eventually what will happen for the sun is it will fuse the helium into carbon and a little bit of oxygen, but then it'll shut off. There just won't be enough mass to compress the core down to start burning oxygen to heavier elements. Although for more massive stars, the process continues and you can keep increasing the amount of pressure in the core, and you can keep fusing these elements into heavier and heavier and heavier elements. But every time you do this, it's diminishing returns. You never get as much energy out from fusing oxygen into neon as you would from hydrogen to helium or helium into carbon. So this is really just the last gas, the very bottom of the gas tank for stars. So when this happens, there's a crossroads about what the next step is. So I'm going to go through a couple of the different scenarios. So for most stars that are less than about 8 times the mass of the sun, which are the most common stars in our galaxy, what will eventually happen is the star will puff up to about 200 times its original size for the sun, larger for larger stars, more massive stars. And then the envelope, the outer layers of the star will be blown away and it'll leave the core remaining. And the core will eventually become a star called a white dwarf. So here are some real images of what this process can look like. So these are called planetary nebula. Turns out they have nothing to do with planets. That's just a historical name. And what you can see here is you have these beautiful patterns of gas. This is the outer layers of the star that have been blown off and are being shot out into space. And we're just lucky enough to happen to catch this happening right as we look at it with our telescopes, like the Hubble telescope here. So you can see these beautiful patterns of gas being blown off, but what you'll also see is that there's a really little dot in the center. And that is the leftover core from the star, which didn't get blown off, which remains in place. And that will eventually become the remnant that we call a white dwarf. Here's another example. This is called the Ring Nebula. It's a very famous planetary nebula. And you can see here, there's another white dwarf, proto-white dwarf in the core in the center of this nebula, which used to be the core of the star, which blasted off these outer layers and created these beautiful gaseous nebula-looking things. So after you blast off the outer layers of a star like a red giant, the core is left there. It's no longer burning hydrogen, but it is hot, and that's just leftover heat from the nuclear fusion that went on for the past billions of years. So white dwarfs are strange objects. They are very massive. A typical white dwarf is about half the mass of the sun. It would have been more massive originally, but it lost a lot of that mass when the outer layers blew off. But it's about the same size as the Earth. And this is an incredibly dense object, therefore. It turns out that the density of a white dwarf is 300,000 times that of the density of Earth. So you can pack a ton of mass, a ton of matter into a very small area. White dwarfs are no longer held up by fusion because they're not doing that. But gravity is still pulling down on them. As I said, they have this tremendous amount of mass. So what's holding them up? And the answer is something called electron degeneracy pressure. Now, this may sound to be a little bit out there, and it's a pretty jargony term, but we're actually relatively familiar with the effects of electron degeneracy pressure. For example, when you walk around, you do not fall through the floor, even though gravity is pulling you towards the center of the Earth at all times. And the reason for that is because the atoms in our bodies have electrons that are orbiting in these shells that are caused by the Schrodinger equation that we solved the Schrodinger equation to see. And these electrons, when they come into contact with other atoms, don't want to go through each other. You can't put two electrons in the same place. They will repel each other. And this repulsion, this distaste for electrons to be packed together so tightly is what holds up white dwarfs. It's also something, it's what holds up white dwarfs, I guess, in a much more extreme way than us on Earth. But there's a very similar phenomenon inside of metals, and that's what makes metals so strong, which is why I'm showing these skyscrapers here. So electron degeneracy pressure is actually not that foreign of a concept. Basically, you just can't pack anything in closer than is possible inside of a white dwarf. The white dwarf is packed so tightly that you can't put electrons any closer together. And that's what's holding it up against gravity. And white dwarfs are much smaller, so they have much less surface area to radiate light, and they're no longer producing their own light from fusion, so they're much fainter. So here's an example of a famous white dwarf. So I'm showing an image from the Hubble telescope again of two stars. One of them is called Sirius A, and one of them is called Sirius B. The A and B mean that these two stars orbit each other. They're binary stars. And Sirius A is the brightest star in the night sky, and it's this big white blob in the center of this image. Sirius B used to be more massive and more bright and more spectacular than even its twin Sirius A. But Sirius B ran out of hydrogen fuel before Sirius A did, lost its outer layers, and it's been cooling down. So even though Sirius B is much, much fainter now, it originally was much more spectacular. After the white dwarf forms, the rest of its lifetime is pretty sedate. It will eventually cool down because it's radiating away the heat from its sort of primordial nuclear furnace. And over time, it will just eventually cool down from a hot, small blue star to a relatively warm, small orange star to a relatively cool, small red star. And eventually it will get so cold that it barely emits any radiation that our eyes can see at all, like you can see in this bottom right panel here. And eventually, it will cool down so much that it no longer has any more energy to release. And at that point, we will call it a black dwarf because it will emit no more light. It's essentially totally black. This will take many, many times longer than the current age of the universe. Every white dwarf that has ever been created still has leftover heat, and quite a bit of it from its original stellar host. So on the HR diagram, here's what this whole process looks like. So let's consider the sun and start here. When the sun is on the main sequence, it stays here for 10 billion years or so. But eventually it will move off in this direction. It will get a little bit cooler and a lot brighter as it becomes a giant star. As it puffs out its area, it becomes much, much larger and gets a little bit cooler as a result. This is because of its changes to the internal fusion structure. It's no longer fusing hydrogen, it's starting to fuse hydrogen in its shell, and it's starting to fuse helium in its core. Then when it starts to lose its outer envelope, it will stay very bright because it will expose its white hot core, but it will lose all of the outer regions, and it will start to move to the blue but stay relatively bright. And then as it starts to cool down, the white dwarf will essentially cool down forever and start moving downwards in this track and move towards cooler temperatures and lower brightness for essentially the rest of time. Okay, so what happens to stars more than 8 solar masses or so? This is where things start to get a little bit more exciting. Now, this is relatively rare. It turns out that lower mass stars are more common than higher mass stars. But these stellar deaths play a really important role in the formation of galaxies and the formation of future stars. So it's important to know how it goes. So when a star that's more than about 8 solar masses runs out of hydrogen, and eventually runs out of the other elements that it was fusing after hydrogen, its core will eventually collapse when fusion ends. So when this happens, the weight of the massive star on top of the core is actually too strong for even electron degeneracy pressure to hold up. So electrons, they will always make sure that they're not near other electrons. But if there's so much pressure, then the only thing they can do is they can merge with protons that are in their counterpart nuclei and turn into neutrons. And neutrons can actually make a much more compact arrangement of matter. So when this happens, if there's too much pressure for electron degeneracy pressure to hold up, gravity will force the core of the star to turn into what we call a neutron star, which is held up by neutron degeneracy pressure instead of electron degeneracy pressure. And neutron degeneracy pressure is stronger than electron degeneracy pressure, so it can hold up higher masses, even though it's being pushed down by more gravity. So this is what we call a neutron star, is this object being held up by neutron degeneracy pressure alone. Neutron stars are even more extreme than white dwarfs. They take all of the mass from a star like the sun, but they compress it into an area about the size of a city. So this is to scale what a neutron star might look like if it was placed next to the skyline of Chicago. You can see the curvature of this neutron star even in this relatively zoomed in image. So neutron stars are incredibly small, incredibly massive, and incredibly dense. And because they're so massive and dense, they have some really extreme physics that goes on. One of the famous things that happens in neutron stars is sometimes they can have magnetic fields that emit light in one particular direction. They can essentially channel light thanks to magnetic fields and electrons that are accelerated by them. And that goes in the direction of their pole, is what it's called. And the neutron star rotates, so you get this beam of light that flashes all across the cosmos. And we can see this when it comes right and points right at us. And we call these pulsars. Originally, when pulsars were discovered, we had no idea what it was. Every few milliseconds, every few thousandth of a second, you would see a pulse of radio light coming from a part of sky that had nothing visible in the optical because the neutron star is so tiny that you cannot see it from optical light. And originally, these were thought to be so bizarre that they couldn't possibly be natural. And they were called LGM, for little green men, because it was, they perhaps jokingly believed that maybe these were aliens trying to communicate with us. So pulsars are one of the extreme outcomes of the neutron star formation. Like white dwarfs, neutron stars will cool down forever and eventually will become cold remnants, just like white dwarfs. Okay, so we've talked about how the neutron star, how the core of the star, as it runs out of energy, collapses down into a neutron star, something held up only by neutron degeneracy pressure. What happens next? We now have this neutron star waiting to emerge from the center of this massive star. And we have all this stuff on top of the neutron star. How does the neutron star get out? So what I'll do is I'll play this video which explains a little bit about how that happens.
The simulations start at the end of a star's life. Having run low on hydrogen, the star starts to contract. An iron core forms at its centre. Matter from the core then collapses under gravity to form a neutron star at its heart. A ball the size of a city, but which packs in more matter than the sun. This is the star's core. Thousands of times smaller than the star itself, but still a few hundred kilometres across. Physicists think that collapsing matter hits the neutron star at the centre, sending a massive shockwave rebounding outwards. You can see the shockwave here in light blue. But then the wave meets more falling matter. It stalls and can't escape the core. The star doesn't explode, and that is where simulations used to end. But today's simulations go much further. Tiny irregularities in the flow of matter can quickly amplify into massive oscillations. These appear as a violent, liquid-like sloshing of matter around the neutron star. Meanwhile, neutrinos, particles produced within the neutron star, ferociously heat up the surrounding matter, causing it to churn and bubble like water on a stove. Eventually, the intense heat of neutrinos combines with the pressure of these violent motions and drives out the shockwave. The wave accelerates out the core and explodes into the star. Though all this takes less than half a second, the wave may take as long as a day to reach the star's surface and create the spectacular fireworks we see. Understanding this mechanism will help astronomers to unpick other important processes in the cosmos, such as how these violent explosions create new atomic elements, which are vital for seeding fresh stars and planets.
So we've talked about what happens for stars that are low mass, stars that are intermediate in mass between the stars that eventually become white dwarfs. But we haven't talked about the very highest mass stars yet. And for these stars, there is no satisfactory outcome. Gravity does win, and eventually the stars and their cores collapse into black holes. They have so much mass that even neutron degeneracy pressure can't hold them up. So when this happens, it can produce a supernova in a similar way to what we just saw. But it's also possible that stars can collapse into black holes without any supernova at all. They just fall in and you're never heard from again. So we're still trying to figure out exactly how this process happens. And this is definitely an active area of research. Can stars just disappear into black holes without producing an explosion as well? Okay, so that was a lot. And we've talked about all different types of stellar evolution. So what I want to do now is I want to show you one final visualization of how the process happens for stars of all different masses and go from start to finish. So this is a simulated set of stars that are all orbiting in a relatively similar part of space and that are all made of about the same stuff. They have about the same amount of elements in the same proportions as each other. And they were all formed at the same time. And what I'm showing here is an HR diagram, a Hertzsprung-Russell diagram, like I showed earlier. And you can see that this green line here is the main sequence. And these dots here are the individual stars that that have been simulated. So we're starting at about 100,000 years. So at this time, the most massive stars, the ones that are the brightest, the ones that are the hottest, are already on the main sequence. They're already burning hydrogen. And the rest of them are starting to collapse down and move on to the main sequence over time. So I'm going to play this video and watch what happens. You can see that as time goes on, stars slowly move onto the main sequence. And The longer, the lower mass the star, the cooler and less luminous, the less bright the star is, the longer it takes to actually fall down and start fusing hydrogen. So by the time that the very last stars are still trying to get onto the main sequence, the very smallest, lowest mass stars are trying to get onto the main sequence, the most massive stars have already started evolving. So that's what's happening up here. You can see that these stars are starting to peel away from the main sequence. They're starting to become a little bit brighter and eventually quite a bit brighter and a lot cooler as well. So as the stars move in this direction, they move upwards and to the right on this diagram, they're becoming red giants. Now, these stars are massive enough that when they become red giants, they disappear off this diagram. They either become neutron stars, which are so tiny and so faint that they're just way below this diagram, or they become black holes and they're not on the diagram at all. They no longer produce any light. So let's continue this for a little bit longer. And you can see that this is happening more and more. And eventually what you'll start to see is a couple of dots over here, down here. So these are the white dwarfs. So what's happened is now we've moved into lower mass stars that are starting to run out of hydrogen fuel and starting to evolve off of the main sequence. So what these do is they come over here, they get brighter and they get redder. They become giants. They hang out here for a while, then they get even much brighter and start looping around here. And you can't even see this on that timeline because it happens so quickly. And they loop down, and then they come back onto this plot here where they start cooling down. And they move downwards and almost parallel to this main sequence and start cooling down for the rest of time. So let's continue and keep going. So watch the timeline up on the upper left. You can see that we're really racing through the ages now. And we're at 19 billion years at this final end of the simulation. So here we're starting to see stars that are cooler than the sun evolve off the main sequence. So these are stars that in real life would never have had time to do that because our universe is only 13 billion years old and we had to wait 19 billion years for the simulation to complete. So this is essentially what happens to stars that were all born at the same time. The younger the star, the more mass the star is, the younger it is when it runs out of fuel and dies. And it just trucks down this main sequence, going to lower and lower masses over time, until eventually we get down to low mass stars, smaller than the sun, which have enough energy or have enough hydrogen fuel to keep burning at their current levels for billions of years, more than the age of the universe.